Emily Washburne will be our next presenter. And Emily, if you can, once you turn on your video, when you're ready, we'll be able to jump to you. Emily, I am going to see, we've got your introduction here. This is the Donnelly Seeps monitoring results. Emily Washburne joins us. She is a water quality analyst from the Idaho Department of Environmental Quality, where she documents a variety of water quality data and fieldwork. Most recently, she has taken part in a study that aims to assess potential nutrient loading from emergent seeps along a section of the Cascade Reservoir shoreline. Emily, take it away.
Thanks so much, Gary. I'm happy to be here. I've been having a few little bandwidth issues, so I'm going to try to nip those in the bud and just turn off my video during the presentation, and I'll be back face-to-face during the question and answer. So thank you for joining me today. I'm going to be presenting results from a seep monitoring project. And I want to mention that this project was a collaboration between the Idaho Department of Environmental Quality and the Bureau of Reclamation. We did the field work and the Bureau of Reclamation provided funding for and completed the lab work. So to get you oriented, here's a map showing Cascade Reservoir in baby blue with Payette Lake to the north. The seeps that we sampled were located along the Lake Fork Arm, which is just to the left of the red dot that represents the town of Donnelly. Cascade Reservoir receives a lot of use. Aside from residential communities, it attracts people who are looking to enjoy its popular fisheries, as well as recreational boating and swimming. The problem here is that the reservoir is eutrophic, so it has a lot of nutrient issues and is nitrogen limited. Phosphorus levels are high, and historically the water body has been impacted by anthropogenic activities related to agriculture, forestry, and urbanization. So a good way to think of nutrient impacts to this reservoir is in terms of the Department of Environmental Quality's designated beneficial uses and the pollutants that impair them. Designating a beneficial use helps us preserve a level of water quality conducive to the activities that a given water body is valued for through the application of protective criteria. These criteria can be narrative or numeric. On top, I've got a table here showing that Cascade Reservoir is designated for salmoniid spawning, primary contact recreation, which by the way refers to activities in which the ingestion of water is likely, such as swimming, and also domestic water supply. These water bodies were all listed in a total maximum daily load report because one or more of their uses are being impaired. And when we look at the identified pollutants causing those impairments in the table below, we see that an excess of total phosphorus is common among all of them. And just really quickly, a total maximum daily load report is kind of like a water quality health plan that's trying to help us get on track for limiting the level of a certain pollutant of concern. So one specific narrative criteria that is often violated in the reservoir is the one that states, surface waters shall be free from excess nutrients that can cause visible slime growths or other nuisance aquatic growths. And this is pretty clearly violated during harmful algae blooms, which affect this area quite often in the summer. To go further back into this reservoir's history of nutrient issues, it was first put on the 303D list of impaired water bodies in 1994. This was in reaction to an infamous harmful algae bloom that occurred in 1993 and killed a number of cattle. Since then, point sources of total phosphorus have been eliminated or reduced through discharge permitting by the Idaho Pollutant Discharge Elimination System. However, intermittent monitoring since 1993 only indicates a slight decrease in total phosphorus, with all originally impaired tributaries remaining impaired and showing little to no change. Since point sources are largely under control, identifying non-point sources of total phosphorus to the system is a top priority for us. Here's a visual of the Department of Environmental Quality's reports related to Cascade Reservoir through the years. Here we're beginning with the 1996 and 1998 TMDLs that were developed because of that 1994 listing. Those reports first established a numeric target for total phosphorus in the reservoir of 0.025 milligrams per liter. The year 2000 is when the implementation plan was written up that proposed best management practices and strategies for meeting goal total phosphorus reductions, and 100% of total phosphorus point source reductions have been achieved. But as of the most recent 5-year review in 2018, we're only at 78% of our goal for total non-point source reductions. And that goal amount is about 11,000 kilograms per year. The seeps first came onto our radar in 2019 when multiple reports came in from concerned citizens noting excessive nuisance plant growth near the 4-H camp beach and around the lake. It was ultimately proposed that nearby wastewater lagoons could be leaking, infiltrating the soil and transporting nutrient-rich outflow to the reservoir via the seeps. In 2020, mounting interest on behalf of Bureau of Reclamation and DEQ resulted in funding for this exploratory study. And here I've got pictures of two of the seeps that we sampled, the two seeps we sampled, the North Seep and the South Seep. And you can kind of see a rivulet of surface flow there at the South Seep, and the North Seep was a little bit more diffuse. In the middle, I've got a picture of a saturated beach zone. So that's looking down from one of the seeps. And you can really see this kind of area of impact here as it connects with the reservoir. So our specific overarching project goals was number one, to assess the nutrient concentrations in the form of total phosphorus, orthophosphates, and total nitrogen that are entering the reservoir from the two selected seep sites and one unnamed creek site. And number two, to determine whether or not there's a connection between water emerging from the seeps and those adjacent wastewater lagoons. Here's a map of our sites in some finer detail of the area. We had 5 sampling events that took place from August to November. We sampled 2 of 4 identified seep sites that are shown here as triangles. And we sampled an unnamed creek above and below the lagoons that drains the area with the land application sites, shown here with the circles. We sampled monitoring wells above and below the lagoons, labeled with the diamonds. And we sampled one of the lagoons as well that was determined to be a good composite of all of the lagoons, as it's the main one used for storage. And now when I'm saying above and below, that's in reference to the groundwater flow path in the area, which moves from the upper right portion of the map down and over towards the reservoir. Here's another map detailing the North Lake Sewer and Water District, showing the areas used for land application outlined in yellow and our intermediate well site at the red cross. On this map, you can also see Boulder Creek, Willow Creek, and Lake Fork, which you'll remember from my impairment slide were impaired for phosphorus. The most important analytes in this study for answering our question were major common ions listed here, which we used to generate what's called a Piper plot and assess the chemical source signatures across all sites, and total phosphorus, orthophosphates, and nitrate plus nitrite as nitrogen. We also looked at E. coli levels and pH, since they both have corresponding criteria that are related to Cascade Reservoir's designated beneficial uses. We also looked at total dissolved solid summation and lab electroconductivity. And I wanted to say we did not select human waste tracers like caffeine or artificial sweeteners. One, because of how expensive they are, and also because they can quickly degrade outside of the septic system, which was a risk of getting a no detection. We also believe that there are potentially multiple sources causing this impairment, and we would have only gotten a presence absent result from those human waste tracers. So the first data that I'm going to share is the E. coli data. We were specifically looking to see if we had any samples above 406 CT per 100 milliliters at the sites that make contact with the reservoir. The reason for this is that is the single sample exceedance for primary contact recreation, and the area right near the seeps and creek are popular for swimming. So as you can see from here, we did not see any exceedances of that single sample. For pH, we wanted to see if the samples fell within the cold water aquatic life criteria of greater than or equal to 6.5 and less than or equal to 9. One sample from the creek above site falls below that, but otherwise everything is in an expected range, including at the wells, which have a lower pH. So we looked at total dissolved solids to see if there was a correlation between the groundwater samples and the seeps, as well as to use it as a general indicator of potential point source or non-point source pollution. As you can see here, the seeps had levels much closer to that of the creek, and then the wells were pretty distinct from each other, with that intermediate well having a higher level of TDS zone. We looked at lab electroconductivity much for the same reason as we looked at the TDS sum, and we saw a similar pattern. There's one major outlier for the South Seep sample event on September 15th, and I truly don't know what is going on there, so that might just be something strange that happened in the field or while collecting the sample. Moving on to nutrients, total nitrogen was in the expected range with one outlier from the creek above site. And on this particular day, there had been lots of melt and runoff, and there was a new intermittent channel connecting to our sample location, which we hadn't seen on any of our previous visits. In the creek below, most of our samples were non-detects, which is not surprising because it is very reservoir influenced and the system is nitrogen limited. We also wanted to look at orthophosphates specifically, since it can sometimes be tied to anthropogenic sources of phosphorus, which can sort of spur on nuisance plant growth. But we did not see any samples outside of the expected range. Again, the one kind of highest hit there is at that creek above, which is a little bit more of like a ditch overall than a creek. For total phosphorus, we were especially interested in seeing how the samples corresponded to the total maximum daily load phosphorus target that had been set of 0.025. And that's what was set for the reservoir and the tributaries. As you can see, this target is exceeded most of the time at both these seeps and those surface sites, being those two creeks. For total phosphorus, we were especially interested in seeing how the samples corresponded to that target. And one thing we wanted to see is we wanted to get a mass load. So what I've got here is historical tributary TP concentrations. And these are averages across all the major tributaries. And the average total phosphorus for that unnamed creek was 0.0546, which is relatively kind of within range of what we've been seeing for other tributaries. We went ahead and we used a 7Q10 flow to estimate our mass load. That's the lowest average 7-day flow from a period of 10 years. We used that mean TP value, and we got this calculation of an estimated load, 0.00072 kilograms per year. For the phosphorus loading estimates at the seeps, we were able to get an average flow, and the average flow at the North Seep was 0.00025 CFS. Average TP was 0.0508, pretty similar to that creek, and the estimated annual load was 0.011416 kilograms per year, a little bit higher, but still very low. At the South Seep, the average flow, 0.002196 CFS, a pretty similar average total phosphorus as those other two sites, 0.0598, and an estimated annual load of 0.11757 kilograms per year. So again, these aren't really high numbers, though these are likely an underestimate, since as you saw from that one picture, the seeps have a pretty diffuse area where they meet the reservoir, and we were only able to sample these kind of concentrated rivulets that were coming off of them.
Hey, Emily, sorry to interrupt you. This is a great presentation. We're cutting into Brian's time a little bit. Do you think you can wrap it up in about a minute?
Yeah, absolutely.
Oh, wow. All right. And again, we'll be sure and share this online. And if people have questions for you, just kind of stay tuned to the Q&A, and you can keep working with the attendees that way. Thank you.
Yep, that sounds good. And can you see this Piper plot slide right now?
Yes, we can.
Okay, great. So we're going to jump to these common ions really quickly. What I wanted to do was generate a Piper plot. It looks a little bit complicated, but here's a slide showing you that what we're looking for is this wastewater signature. So I'm looking for sites that are going to fall out in the highlighted portions of that graph. And the sites that fall out there are the intermediate well, the lagoon itself, and then kind of the up gradient well falls out. And so as we go through and we look, we see that the seeps and lagoons are pretty distinct. Seeps and wells, also distinct. The creek, we've got one creek signature. This red dot is migrating towards the middle. So that kind of makes us wonder, is there some sort of influence from the lagoons? And then we look at the well and lagoons, and we see that that intermediate well, which is at that land application site, does appear to be slightly influenced. So what we go ahead and did was we used a stiff plot. A stiff plot kind of shows you the chemical constituents as a shape. So it lets you see if there's some direct correlation between your sites. And our really big takeaway here is that the lagoon does not appear to be contributing to the constituents in the creek below or those seeps, and that the creek and seep constituent concentrations are relatively dilute. And I've got those kind of circled there so you can see that connection. So our big takeaway is that site sample did not appear to be a significant source of nutrient loading to the system, although total phosphorus targets are exceeded at all sites that connect to the reservoir. So still a good candidate for continued BMPs. Wastewater effluent signature was not present in the seep or creek outflow, so those lagoons do not appear to be impacting the reservoir via these surface water sites. Looking forward to next steps, I think a really big question here is about internal phosphorus loading versus external, since it seems like a lot of point source and non-point source discharges are being brought under control. Just wanted to say a special thanks to everyone that made this possible. And I've got a moment here if there are some questions.
Excellent. Thank you, Emily.
Yeah.
What we're going to do is if people have questions for Emily, please put them in the Q&A. And Emily, if you can access that from your panelist window, you should be able to type a response.